Hey y'all, it's Andrew Couch here, and in this Tidy Tuesday video, we're actually not going to look at this week's data set again. I know I've been kind of deviating away from these weekly data sets, but I found that a lot of you guys want to do a lot of Tidy model stuff, and I thought it'd be interesting to kind of go over a book that I've been reading in the past week called Feature Engineering and Selection: A Practical Approach for Predictive Models. And Max Khun actually, I guess, like co-wrote this book, and it's actually the successor to Applied Predictive Modeling, which is a machine learning book. Which, let me grab it. Which is this book right here that I read last summer, and it really taught me a lot about machine learning. Max Khun also is a pretty busy guy, and he's working on he's on the TidyModels project too. So I figured that since I kind of taught basically kind of the model procedures of applied predictive modeling and the Tidy framework, I thought we should go more in depth into more feature engineering. I think 2 weeks ago we did some feature engineering stuff, specifically imputation, standard scaling, and that kind of stuff. But we didn't really do any uh, any advanced feature engineering. So with this book, I actually was reading let's see here, the interaction effect section, and I thought that'd be a pretty useful thing to do because once we already have these centering and scaling and PCA and all this linear combination stuff, we should actually kind of look into some actual analytics and kind of science and statistics into these actual models. So I think for this video, I'm going to basically center around interaction effects and how to create them in the TidyModels framework. We'll also do it in the linear model or the base R section, but for right now, we're going to do it in TidyModels. So let's look up a R Markdown. I'm going to do this a GitHub document, make this full screen. I'm going to zoom this in a little bit. There we go. Okay. Oops. And we're actually going to use a decent amount of packages, but we're not going to do a lot of data visualizations. And I'm going to try to make this a little quicker, but we should be still learning a few things. So let's do the TidyModels package, the Tidyverse, and also this package called the Ames housing package. And what's cool about the Ames housing package is it's essentially like it's essentially just a data set. So we're just going to do that. We'll call this the Ames data. Cool. So when we look at Ames data, we can see that there's a lot of columns and a lot of rows. There's about 3,000 rows and 81 columns, which actually means it's a pretty wide data set. It's not one of these toy data sets. Well, it is a toy data set, but it's not one of those toy data sets like Iris, right, where you can kind of easily visualize it. This will actually take a lot of time to visualize it, and we can kind of see there's a decent amount of factors, right, or a bunch of categorical variables. There's a few I guess numerical data. What I also noticed is, okay, it's a bunch of scales too, right? So we have a bunch of like ones and twos and also 1600s. And the main thing and we also have longitude, latitude data. So we have like geospatial stuff. But the main thing that we want to look at for this data set is sale price. We're actually going to be using TidyModels to predict sales price. So let's just look at the distribution of it. So sales price. Sale price, and then let's just do a ggplot sale price, and then let's do a histogram. Let's do a histogram first. Let's do a SciPen first. Options SciPen equals 999. Cool. So let's look at it. So the median price is about $200,000, like less than $200,000. That makes sense. I actually lived in Ames for a year when I was at Iowa State. I think I mentioned that before, and all those houses are not too expensive, but we can see it's kind of centered around there. Okay. So I'm not actually gonna do a crazy exploratory analysis on this stuff. I've actually kind of looked at this data set beforehand to kind of prepare this lesson or video. So when we think about interaction effects, like what are interaction effects, right? And the main idea between interaction effects is that that when held equal, they contribute something to explain some type of variance. However, what they really do have is an interaction between another feature. So it's saying that when one feature changes, the other feature is also affected. And a good real world example that I believe is used in this book is the idea between like saying we're going to create a model to predict crop yield, and one of the features is rain, and the other feature is fertilizer. So we know with crop yield, when that rain's pretty good for crops, right? Fertilizer is pretty good for crops, but if we put fertilizer and we have zero rain, you can add as much fertilizer as you want. You're not going to get a lot of yield. And same thing with rain. If you add a lot of rain, there's going to be some diminishing returns without the fertilizer. So fertilizer and rain would have an interaction effect when creating a model to predict crop yield. So let's see if there's any interaction effects in the Ames data. Okay, so I already know that there's one interaction effect. I'm just going to do it with its relationship to sale price. So we're trying to think, what interactions do we think would affect sale price? And one of the interactions that is used is the year built and central air. Okay, and for the crop example, that's actually using continuous variables. And actually, continuous variables is kind of hard to visualize those type of relationships. Like if you think about it, how could you visualize this? You couldn't do an XY scatter plot. Maybe you could do like sizing too, but the easiest way to do it is to compare the interaction between a factor and a continuous variable. So that's what we're going to do. ggplot, AES, X equals year built, Y equals sale price, color equals central air, point plus GM, smooth. And since we're kind of thinking about like we'll control for these factors, we'll just do a method equals LM. Okay, cool. I'm going to turn the alpha down. Alpha, was it up or down? 0.1. Okay, and we can see here. So one main thing with interaction effects, especially with these like, factors and continuous variables, is that how you can really tell if there's appears to be an interaction, or we're not doing a lot of causal inference, but we're seeing interactions will generally have this kind of like crossing where the slopes are different. A non-interaction, or if we think that these values weren't interacting, we kind of see that they were parallel, where there'd be like no effect on sale price. Whereas if we see with central air and year built, we can see that they have different slopes. For the no central air, it kind of seems like it's almost zero slope. It's kind of staying stagnant. Whereas the central air, yes, we can see that it's actually increasing as the home is newer. And let's actually look at it separately, right? So I'm going to do that. I'm going to select this. Okay, and we're just going to do a ggplot. We'll do what's it? Maybe a gather key equals key, value equals value, minus sale price. And then we can do a ggplot, AES, X equals value, Y equals sale price. And then we'll do a plus GM. Oh, actually, we can't do that. How can we do this? Okay, we'll just do that. So year built, and we'll just do that as a function of ggplot. Yes, X equals year built, Y equals sale price, GM line. Okay, we got that. So we can see this kind of like scatter plot thing. We can see how as year built, as these houses are getting younger, their price is going to be it's going to be increasing. And if we look at the other one where we do select sale price, and then we select what was it, central air, ggplot, AES, X equals central air, Y equals sale price, and then let's do like, I don't know, a box plot, right? We can see how there's definitely a difference between the sale price. We can see how there's a difference right there, and then we can see the actual interactions and how no central error has less of an interaction than we actually would have expected. Okay, cool. So now that we have this type of stuff, let's try to do this in like in base R. I'll just do the base R first, just to make it so we can kind of get some intuition and just see how easy it actually is. So we can do, let's see here. If we just do a linear model where we want to predict sale price, price and data equals aims data, we can see that there's a lot of features. And not only that, if we notice, the linear model will actually automatically like change these factors into dummy variables, right? So we're gonna have to think of something where like, okay, well, we could do like a tidy and kind of get all this stuff, and we can evaluate our p values. You know, we could say like filter p dot value is less than or equal to 0.05, right? And we have 92 features, and we can just do like all the interactions that are statistically significant and just start from there. But I think what we should kind of look at is let's kind of look at them individually. So let's kind of select first the continuous variables, and then we'll select the categorical variables and create some models and figure out which ones are statistically significant, combine them together, and then let's start counting out the interactions. So how are we going to do that? Okay, so let's just say this seems like a lot of work and might not pan out. Okay, so let's do that. Say let's select the numerical features first and create a model. Because if you think about it, we could do all the interactions possible, all these pairwise interactions. So if we do aims data, column names, we can see that there's 81 column names. But if you think of 81 pairwise features, or like 81 combinations, is actually a lot. I think I saw with the formula, it's like 81 minus n minus 1 divided by 2. Wait, no, it's like 80, like what, times it or something like that. But there's a lot of features. It's not like with the iris data set where we could just do, oh yeah, there's what, 4 features, so we could just do a simple model and calculate all the pairwise combinations. Actually, maybe I'll make all the pairwise combinations just to show you how easy it is, but how honestly it's not a good idea to do it. So if we do that times, I think this data equals iris, right? Yeah, and then we can do what? Yeah. Okay, species versus. Okay, yeah. Oh yeah, I think it'd be easier if I just tidy it. So it's calculating. Say you have our, since we're trying to predict sepal length, it has sepal width, petal length, petal width, species. Since it's dummied, we only have 2 of the species, and then has sepal width times petal length, sepal width times petal width, sepal width times the colors, and we have all these combinations, right? And if you think about it, if we only had, what is it? 1, 2, 3, 4. If we only had 4 features and generated like essentially 15 features, or I guess for 10 more features, that's kind of a lot. So we're not going to do that. That seems like a bad idea to do it. So we're not going to do it. So I'm going to say can't just generate all pairwise combinations when there is a lot of features. Okay. So I'm going to do that. Okay, so let's do that. Let's find the numerical features first. So we can do a select. I think we can either do select if and say is dot numeric, right? And it'll select all the numeric features. One thing that I found that we can also do is select and say where is dot numeric, and we can also do like sale price. So we can select sale price first, and then where is dot numeric. So now we have all these things. They're doing the same thing, but when we do the factored variables, we can kind of add sale price first and then do say where is dot factor. So that makes it a little bit cleaner. So we can do that. Where is dot factor? Right. So we have all that stuff. That's cool. Okay. So let's first do this. First, we'll say generate a model with only numerical features. Oh, features. Okay, so we'll do that, and we'll do a linear model, sale price, data equals dots. Then we can do a tidy. We can do a filter where the p value is less than or equal to 0.05. Just gonna make sure it's yep. That's 0.05. Then we can do a select the term. Cool. And then we can say let's see here, numerical features that we want to use. Okay, so now we have these guys. If we we're gonna run into a problem here. If we do a linear model where we do sale price, where we do the same thing, right? Data equals dot tidy filter p dot value is less than or equal to 0.05. If we look at this, this isn't great because it's saying, you see these things, these are the same column, but since they made a dummy variable, we can't just select a term and say, oh, we're going to select these variables, right? We kind of have to do some cleaning. So here's what I'm going to do. I'm going to say, rename if is dot factor dot funds equals, and then we'll say paste paste dot, and then the separation, we'll say separation is just that, and then we'll basically give it this ending so we can tell that, oh yeah, here's the start of the actual values from that column. So we're gonna do that, sep equals, boom. Let's see if that worked. There we go. So now we have all of these factored variables or factored column names has kind of like this this little pointer that can say, okay, anything to the left of this is from this class or from this column. Okay, so we're gonna do that. Cool. So now we have all of our features that we want. Okay, if you know, that's like 85 features. That's a lot of features. But just know that, well, this one is technically just one column, right? So we don't have to worry about it too much. And then what we can do is we can just do some regular expression. So we'll say term, but we'll say we'll say select term, and then we'll do like a mutate new term equals str replace all. The string is a term. The pattern is, we're gonna do an escape that dot, and then just do that. Okay, cool. And this base says like, okay, once we find this thing, we're gonna go until the end and just replace it with nothing. Cool. And also I'm gonna change the new term equals str replace new term, and then we want to remove this little thing right there. I'm not sure if it actually matters, but we're just gonna remove it. Okay, select new term. Okay. So now that we have our terms, so I'm gonna give this thing and call this categorical features. Categorical features. Okay. Generate a model with only categorical features. So we have these features, right? So now we can do another little cool tidy select thing and say aims data select sale price, any of, and we can say numerical features, and we have to say was it term, and we selected all that, right? We can also, I think, add another one, any of, and then we can say categorical features, and then was it new term. Cool. So now I think we have all that stuff. Yep. Good stuff. And what we're going to call is we'll call this our, let's call our main effects data. So right now we're just trying to create a main effects model. So we're just trying to make a baseline model with no interaction effects. But we did do a lot of reduction. So we removed a lot of features we didn't think were going to be very useful for us. And in this case, we used the p-value criteria. So there's actually some problems that I think we kind of did with the p-values. For one thing, I think we should have standardized them, which actually isn't too bad to do. Let me see if I can do a standardization of it. So if we can just do I think, what is it? Summarize, adjust, what p-value? Dot p-value? What is it? P-value edge dot p-value. I think it's something. It's adjust dot adjust p-value r. P dot adjust. Okay, p dot. Okay, that was really annoying. Okay, so p dot adjust. So we can do like a p dot adjust, and then we can p dot value, and then we can say method equals false discovery rate. Right. New. We can say like adjusted p value equals that. Right. So we have our adjusted p value, and then we could do something else like that. I think we can say also dot equals false. Oh well. So that's kind of how you you know how to. I'm sure there's like a thing with the summarize function. Summarize. Let's see here. Minus summarize. Question mark summarize. Oops. Summarize. Dropping. Oh, it's I think keep equals true. Cool. So we can do what is it? Keep equals true. I don't know. Whatever. There's probably a function that you can keep it. Okay. So now that we have the main effects data, we can kind of move on and do and start creating our interaction effects. Okay. So I think this is when we're actually going to bring some TidyModel stuff. One thing that we can do though is let's see here. How can I do this? Is when we're creating our interaction effects, we could actually do we should probably specify our main which features are actual categorical features and which ones are numerical features. So how are we going to do that? Let's see here. Main effects data rename if is dot numeric is dot we'll do is dot numeric dot funds equals, and then we'll say paste a dot, and then we'll say dummy. We'll say underscore dummy. Separation equals, yeah, no separation. Let's see if that worked. Year build dot is dot what is it, factor. Cool. Then we can do rename if is dot numeric dot funds equals paste dot numeric sep equals, and then we'll say rename sale price equals 1. What's here? Oh, so I just so at first sale price would be sale price underscore numeric, and now I just changed it to sale price. So now everything's kind of situated. So I'm going to give that to the main effects data. Cool. Okay. So we can say created data for modeling, renamed columns for each feature data type. Cool. So let's start doing some tidy model stuff. Okay, this is where it's kind of good. We'll say set.seed equals what is it, 2020? So 2020, and we'll do a main effects model and main effect and an initial model. Okay, so let's do that. So we'll say main main split initial split main effects data prop equals 0.8. Now that I think about it, we don't even have to, we could just use the same splits, right? So let's just do that. We'll just say tidy split. Tidy split. Tidy train equals training. Tidy split. Tidy test. Testing. Tidy test. Tidy split. Cool. And I'm gonna run that just to make sure I do that. So create, train, and test splits. Create k folds. It's just great. So tidy k folds. V fold CV. Tidy train. And we'll keep that. Okay, cool. So we have our train, we have our data stuff. We did a basic look at an interaction effect. Let's start doing this. So yeah, let's do it. So let's create first our main effects model, main effects recipe. And this is one where we just are not doing anything. We're not creating any interactions. We're just doing some basic pre-processing. So we're just gonna do that. So data equals tidy train, and we'll say step dummy, and we'll say all nominal, and then step center, and they'll be all predictors. Cool. So we have our main effects recipe. Nothing going on too much. We're just kind of doing a center on all the variables. Nothing too crazy. So then let's do a main. We'll do interaction. Let's start doing our interaction effects. So create basic recipe for a main effects model / baseline. Okay, now let's say create the interactions. Okay, so let's do a recipe. Sale price data equals tidy train, step dummy all nominal. And now what we're gonna do is we kind of have a problem that when I was looking at interaction effects, I didn't really think about it. But while I was reading the book, they made it a point to say you generally should create your interaction effects before you center and scale. Okay, because once you center and scale or center your data, it kind of loses all of the actual interaction effects between the variables. So we need to make sure to create the interaction effects before our step center. Also, one of the reasons why we're not scaling is for some reason when I do step scale, it messes with the GLM net model that I'm going to do in the next section. I'm not sure why, but it's fine if we just center it. So let's first start doing the interactions. So if you notice, since we have our our main effects data, we have all these things where we have like numeric and stuff like that, and then we also have our dummy ones. And since what we're gonna just do is we're gonna do the interactions purely between our factored and numerical data, and not just all the combinations. We can do some things that we can use some tidy eval functions to help us make these interactions. So that's what we're gonna do. We're gonna do step interact, and we give it a formula with a little tilde, and we'll say contains dummy, and then we're going to do the colon and say contains numeric. Cool. And then what we're going to do is we're going to say step center all predictors. Cool. All right, and we'll call this our interaction effects recipe. So if you actually look at it, if we do the interaction effects recipe, do a little prep, it kind of loads a little bit because it's trying to calculate all the interactions. Okay. Oops. So we see all these things. It's saying, okay, we're going to create the dummy variables. We're going to do the interactions with all of these dummy variables and compare it to, I guess, all of these numeric variables. Okay, and then we're going to center it. If we do a bake and we just give it the tidy terrain, and then we give it the column names, we can kind of do a sanity check just to make sure that it's working on it. Technically, I could have just did like a head function right here, and it would probably went faster. So what do we see here? We can see all of our numeric stuff. We can see how it created the dummy variable. We can keep on going down. Let's go here. And let's see if there's an interaction set. And then we have our interaction right here. It's saying dummy 1 story 1945 and older times the lot frontage. Cool. So we have our interactions. Let's see here. Can we do a n row? Okay, we can't. Oh, I bet it's length. Just that. And then I'll do let's do a head. So now there's 4,800 features. That's a lot of features. And that's something where we have more features than our actual samples. And that's a big problem. That means that we really can't use a linear regression right now. So how can we really reduce these interaction effects? One of the main things from this book is that one of the ideas is interaction effects. Only some interaction effects will actually add value to our model. Okay, and the point is, our models really shouldn't have like 3,000 interaction effects. In reality, I bet only about like 5 or 10 of them will actually add a lot of value, or there's like some type of diminishing returns onto our explained variance in our model. Okay, so what we're gonna do is, if we have a lot of features and we want to remove them, what that always begs me to use is a lasso regression model. So that's what we're gonna probably do. Okay, so I'm gonna make a comment and say that's a lot of features. We will need to do some feature elimination. Okay, so let's create our lasso model. So let's create a lasso model. So lasso model linear regression. Linear regression. Penalty. Since the penalty, we'll be tuning that, but we know that our mixture needs to be 1. Mixture equals 1, because mixture equals 1 means it's a lasso regression. So we'll do set mode equals progression, and we'll do a set engine, and that engine will be GLM net. One cool thing that I was kind of looking at is we don't actually have to even define our parameters for our like tune grid. So we can just say define model parameters, and we can just say lasso info parameters, and we can say lasso model, and that'll actually just give us the things that we're going to be changing. Here's penalty. Cool. Okay. So now let's start creating our workflows. So create the workflows. So first we're going to say our main what did I call it? Main effects model workflow. So we'll call this main WF workflow, add recipe, main effects recipe, and we'll say add model, a lasso model. Cool. And we'll say interaction effects model workflow. We'll call this int workflow, add recipe, interaction effects recipe, add model, and we're going to give it the same lasso model. Great. So we kind of have our model workflow, our model workflows. Now let's actually start doing the tuning for our models. So we're going to do let's say create the tune grid for the models. And since we're using the same models for both of our workflows, we can just use the same grid. So we're going to create a lasso grid, and we'll say grid regular. And instead of saying like penalty, we can just say I can just pass on the lasso info, which will give it the parameters that we want to change, and we'll say levels equals let's see, we'll give it 15 different tuning parameters. 15 different types of penalties that we want to use for it. Cool. Okay, so now start tuning them. So we'll say tune models using grid search. So and we'll say we'll do main the results first. Main results equals tune grid. Give it the main workflow. Give it the resamples, which is the tidy folds, and give it our grid. And our grid is equal to our lasso grid. And we're gonna do the other one too. I feel like there's a way to do to maybe do some things where it's more automated, but we only have to switch one thing, which makes me suspect that we can do it, but I'm not sure how to do it yet. So int, and then we're gonna tune these models. Okay. Let's see here. What else do we need to do? And what's cool is when we pull up my OneNote app, what's cool I took some notes behind it, and we can kind of go over yeah. Oh no, get out of here. Okay. Sorry about that. And there's basically some ways to do, there's some principles, and one of the main things that there is the hierarchy principle. Let me see, how do I zoom in on this? How do I was it view? Oh, there you go. So there's the hierarchy principle, which is the higher degree of interactions, the less likely the interaction will explain variation. So in this case, we're doing a low hierarchy. We're doing a low degree of interactions. When we're doing a pairwise interaction or with two features, that's considered like a 2-degree, I think, interaction. What they're explaining, what they're basically saying is that it's not realistic for you to use like 5-way interactions where it's gonna be like if, for example, if we're gonna go back towards like the crop yield example, it's not gonna be an interaction between sun, rain, fertilizer, humidity, all those together. it's probably not going to add that much value opposed to having two different pairwise interactions. Okay. Additionally, there's another things of effect sparsity. So they said like, okay, just only some of them will, like, even if it's possible to use them and you see that they're available, it probably won't. It might not actually explain the variations. One of the main things is the heredity principle, which means that, which is the idea of interacting terms must be statistically significant. Okay. There's two different types of heredity principles. There's strong heredity, which means that if you're doing a pairwise interaction, both features need to be statistically significant. So we would say like both of these features that we use in our pairwise interaction must have p-values lower than 0.05, less than or equal to 0.05. A weak heredity means that only one of them. So if one of the features needs to be statistically significant. So so you can have one strong where it's like the p-value is less than or equal to 0.05, and the other one could not be statistically significant. Since we're really trying to reduce the amount of features we have and the amount of interactions, we actually use a strong heredity principle. Cool. So we have all of these things. We can just find out the main tunes. So we could say main tune. I'm actually skipping like, okay, let's do a model post hoc on this stuff because we're actually kind of using this to kind of explain some things and kind of go over these tidy workflows that I haven't really gone over. So if we do like, so we can do a main tune and we can say like main results select best, and we probably want RMSC as a metric. So we'll say extract model parameter. So we got our main tune and we got our interaction tune, right? So int res, boom. Oh, int. Okay, so we have our tunes, and if we can probably look at our main tune and our int tune. So they have basically the same penalty parameters. Interesting. Okay. Additionally, what we can do is we can kind of create our final workflow. And this is something where I've finally been kind of looking at the workflows and slightly wrapping my head around it. So we're going to do this. This is something that's probably going to be useful, especially when we're doing these lasso regressions. So we're going to do that. So finalize the workflow for modeling. Okay, so main workflow, finalize a workflow and give it our final tune. And we can do our int workflow, finalize workflow, int tune. If you notice, in the past videos, I was actually creating another workflow. And here you can just assign the final parameters to your original workflow, which is actually very convenient. So that's what we're gonna now look at our final models. So we're gonna do that main workflow, last fit, main split, collect metrics. Okay, so we have our root mean squared error or 30,810. Okay, and then we can do it int workflow, and we can do it main. What is it called? What do you call it? Main split, right? So get test metrics. Okay. Whoa, actually just said. What are we trying to do? Sale price, yeah, okay. Okay, cool. So we can see that they're slightly different. But what we can do is now we do kind of like a post hoc on our model. Because if we actually look at our workflow, we see it, okay, it's doing linear regression, it's just doing a dummy and center, using a penalty of 0.0001 mixture of 1. If we do our int workflow, it's doing the same thing. It says, okay, we're also adding an interaction, yada yada, nothing crazy. Okay, but what we can actually do is what we want to do is extract the model and kind of look at its coefficients, right? So let's do that with our first model. So we're gonna do like a post main model, and we'll say pull workflow fit, and we're gonna do the main what's called let's see here. Oh yeah. What am I doing? Sorry, I totally got ahead of myself. What we have to do now is actually create our final model. So we're gonna do that. We're gonna say main effects. So now we're gonna say create our final model. Since right now we just created our workflow, but we haven't actually created a model yet. So that's what we're gonna say main effects model. We're gonna fit our main workflow with our main effects data. Main effects data. And then we're going to do our interaction effects model, and we're going to fit that with our interaction workflow and our main effects data. Okay. Create our final models. So if you look at our main effect model, it's kind of just showing you our workflow. So we did a linear regression, dummy tail has a little thing, great. But that's not actually showing our coefficients. We kind of have our tuning parameters, but we don't have our coefficients. So what we got to do is we got to pull our workflow fit. Okay, and this would be our post main model. And we look at our post main model. We can use the pluck option and pluck the fit. And we can also do finally use the coefficients thing. But if you look at it, there's actually 225 different coefficients. Right, that's kind of a problem. And we can see our coefficients, but we kind of don't know what, like, we don't want all of these tuning parameters, right? So what we can do is we can specify our coefficient with s equals, and we can specify our best tuned model. In this case, we can use the main tune, right? Main tune penalty. Okay, and we have all this stuff. So now let's actually look at our interaction effects model. So let's do a post interaction model. Pull workflow fits our interaction effects model. And then with our post int model, we'll do a pull workflow interaction. Oh no, not. We'll do a pluck fit coef s equals what is it? Interaction. What do we call it again? What is it? Int tune. That's what it is. Int tune. Int tune with the penalty. And what do we see here? We see that it actually did eliminate a lot of our features, right? So right now, what we can do is we can just do like, was it a tidy, right? So with the main effects model, we have so with the interaction effects model, we only have 356 features now. And then with the post, with the actual main effects model, we have 224. So we did do a bunch of We did do a bunch of reduction in feature elimination, or we did a decent amount of feature selection with our lasso regression model. We shrunk our 4,848 features to was it 356. So yeah, this is basically this is kind of a short, quick video, but I wanted to do a something on interactions just so you could do a little bit more advanced feature engineering. Um, I'm still getting a hang of these workflows and all these cool little like pluck options, pull workflow fit, and stuff like that. But I'm definitely getting better at TidyModels. I definitely understand the workflow now. I'm using less variables, and my environment's less cluttered. So I'm sure I'll probably make another TidyModels video in the future. Until then, tidy on.